Oh, good afternoon. This is Structural Analysis Made Fun and Easy. This is part 2 of Simply Supported Single Span Beam with Single Point Load, Mid-Span Point Load. In part 1 we looked at the reactions and we found the moment. We've set up the equation for the moment. So let's carry on where we left off on the last video. So EI equals d2y over dx squared. EI d2y over dx squared equals px over 2. Let's take our EI on the left hand side until the end to make it life a bit easier. So now we need to integrate. The first step is, so this equation d2y over dx2 is equal to m. So to get the slope, we need to integrate the equation so we can get dy over dx, which equals the slope. So the integral of d2y over dx2 px over 2 is dy over dx equals px 1 plus 1. Then divided that by 2, the original 2, divided that by 1 plus 1, so that's 2, plus the integration constant that we don't know, c1. c1 is called the integration constant. I'll make it a bit bigger actually than you. There we go, that's better. So d2y over dx2 is equal to px over 2. Sorry, the minuses we've eliminated the minuses. C1 is called the integration constant. dy over dx equals px squared over 2 times 2 plus c1. Therefore, dy over dx, which is the slope is dy over dx. That's the first differential of y. Remember that y is the deflection. Dy over dx is obviously, if you drew a straight line where the deflection was at the angle where the beam was, the angle of deflection, that's basically dy over dx, isn't it? It's obvious when you think of it. So if you had a beam that deflected 10 centimeters and it was dy, and the beam was 100 centimeters long, so then dy over dx would be 10 over 100, so you'd have 10 over 100. So that's also the gradient of the slope. 10 over 100 would equal 10. So that actually, yeah, there's a good point in that this, I do not believe that dy over dx is an angle, it's a ratio. So dy over dx equals px squared over 4 plus c1. So that's the most important thing to remember. So we've got m is equal to px over 2 and slope equals equal to px squared over 4 plus c1. Okay, so what is the value of c1? As you probably guessed already, some of you have watched the other videos, what we've got to do now is we use our boundary conditions. So this equation is the slope. We know that at the middle the slope is 0 because the beam is symmetrically loaded. Therefore, when x equals L over 2, the slope is equal to 0. Well, it's not degrees, it's actually a ratio. It could be, it's not even radians, is it? It's a ratio. So dy over dx equals to p, and then so we've got to put L equals 2 where we had x in the above equation. Now we've got to put p, instead of x squared, we're going to put L over 2 squared. So p L over 2 squared divided by 4 plus c1. Where slope is 0, that's at the middle, equals to dy over dx equals 0, where it's in the middle. Therefore 0 equals pl squared over 4.2 squared plus c1. So pl squared divided by 4 times 2 squared. 2 squared is 4, so 4 times 4 is 16. 0 equals PL squared divided by 16 plus C1. So if we rearrange this, then we take the PL part to the other side. C1 equals minus P times L squared over 16. So the integration constant is minus PL squared over 16. So if we want to just have a final equation for the slope throughout the beam, let's now put back EI back, because we took it out just for convenience. So EI would go back on the left hand side. So if we want to take it to the right hand side, we've got to divide both terms by EI. That means that dy over dx equals p x squared over 4 EI minus PL squared over 16 EI. So this is, you can see that we got one on the right hand side, we got one term that is fixed because L is fixed and P is fixed, and one term where X, so this is the variable part of the equation, the first part. So now we have a consistent equation for slope. We need to integrate again. So now that we've got the slope, we need to integrate again, second integration, to find the deflection. Let's take out EI again to save time and energy. So now we've got dy over dx, now we want to find y. So y is equal to the integral of dy over dx equals to the integral of, I'm sorry about the dot, I just need to get rid of that, but yeah, it comes up with that otherwise. Px squared over 4 minus PL squared over 16. Therefore y is equal to px2 plus 1 divided by 4 divided by 2 plus 1, which is the same as the x exponential, minus PL, in this equation x is 0 because x to the power of 0 is 1. So I suppose I could put that on just to, oh yeah, I just put that on for you so it's clearer. It's the same thing there, because x to the power of 0 is 1, so that's this PL squared divided by 16 is the same as PL squared 16 x to the power of 0 because it's 1. So I'll just do that again. Y is equal to px squared plus 1 divided by 4 divided by 2 plus 1 minus PL squared times x 0 plus 1 divided by 16 0 plus 1 plus C2, which is the second integration constant. Therefore y equals to px cubed divided by 4 times 3 minus PL squared x to the power of 1 16 times 1 plus C2. Okay, so now we add E1, and let's take E1 to the right. Sorry, not E1, EI. Okay, so now we add EI, and let's take EI to the right. So again, y equals px cubed divided by 12 EI minus PL squared x divided by 16 EI plus C2. Call that equation 9. So that's y, the deflection. Okay, so what value is the value of C2? Yeah, again, we use our boundary condition. So this equation is the deflection. We know that at the support the deflection is 0 because the end condition is fixed. Let's take out EI again. Therefore, when x equals 0, deflection equals 0, y equals 0. Therefore, y, as per this equation, y equals px cubed, so that will be 0, minus PL squared times 0 divided by 16, that's 0, 0. So 0 equals 0 minus 0 plus, so C2, that has got to be 0. So to complete this, we simply insert, so we got C2 was 0, that means we've got a consistent comprehensive solution for y. Y is equal to px cubed divided by 12 EI minus PL squared x divided by 16 EI, equation 9. Okay, so it's very simple. It's really, really easy, isn't it, obviously? I know these, like, this video has probably been done 100 times before, but I just wanted to give, my explanation of it, because I think some of those videos aren't that good. So yeah, if anyone who doesn't believe this, and just to check, because we have time on our side here. So there is another boundary condition we can check where you might be saying, why didn't he check x equals L, because y equals 0 when x equals L? But the thing was, when we get past L over 2 in the span, the moment changes. So then we would have to rewrite from equation 10 onwards. So instead of having m equals minus p times x over 2, when we get past x, when x is greater than L over 2, then m equals minus p x over 2, and then it's going to be plus p times x minus L over 2, because the lever arm will then be x minus L over 2. So you can't. So the value of m that I put only is correct only till x equals L over 2. But so what I do is I'm going to do another sub video on this. So please see my other video for this, as otherwise the video will be too long. But please be assured this is correct, as I've done this already and it works. Please see the separate video. So I will do another video where we could check. I just have to do it again. I just have to start back from equation 10 will be different, so that means everything above will be different, but it will give you the same answer. Please see my other video for this, so that will be a separate video. So at the moment we've used boundary condition x equals 0, so we've found out what y is. Okay, so now we want to know what y is when x equals L over 2. So we put x equals L over 2 into equation 8. That gives us x equals, y. We want to know y when x equals L over 2. So you put x equals L over 2 in equation 8. Y equals p L over 2 cubed divided by 12 EI minus p L squared times L over 2, 16 EI. P L squared, that's going to be x is L over 2 over 16 EI. Therefore y is equal to p L cubed divided by 12 EI, 2 to the power of 3. So 2 to the power of 3 is 2 times 2, which is 4 times 2, which is 8, minus p L squared L divided by 16 EI times 2, because L over 2, L divided by 2, so the 2 goes to the bottom. That gives you y equals to p L cubed divided by 12 EI times 8, p minus p L cubed 32 EI. I don't know why I've put that back. So, oops. So y is equal to p L cubed divided by 96 EI minus p L cubed over 32 EI. That is equal to y equals p L cubed over 96 EI minus 3p L squared. Done again. So I've gone backwards there. So y is equal to p L cubed divided by 96 EI minus 3p L cubed divided by 96i equals, and that equals to minus 2p L cubed over 96 EI. And 2 over 96 is equal to 1 over 48. So therefore y equals minus p L cubed divided by 48 EI, which is probably, as you know, widely known to be the maximum deflection at the middle of a simply supported span with a point load at the centre. So this is all. I guess actually, if you haven't done it a few times, it can be quite confusing. It's easy to go wrong, I guess. So it was worth doing the video. So this is for more experienced people. This was very easy and very basic. but it's really essential to know the basics of structural analysis. So the deflection is minus PL cubed over 48 EI. So I hope this helped you out. Hopefully, if you found this video useful, there's loads more of videos that I've done that could also help you in structural analysis and design. Some of them go into reinforced concrete design, done steelwork design. I'm going to do some more on timber. I just need a bit more time to get them sorted out. Check out all my other videos on structural analysis made fun and easy on YouTube. Please like the video and subscribe to the channel. Donate if possible for more videos like this for BEng Honours, MEng, MSc, HNC, HND, Civil Engineering courses, Theory of Structures. All this is like should be really useful for people like just starting university courses as well for 2021. Hopefully you'll find it easy now to get past the exam or coursework or whatever. If you've got any questions though, please feel free to leave comments in the section, and I'll answer them. Or if you wanted more help, then please email me using the contact details. Thanks a lot for watching. I hope you enjoyed this video.